In the following video, we're going to take a look at some of the equations we can use to solve problems about the partial pressures of gases. The first equation allows us to do a calculation on the total pressure in a system based on the total number of particles in our system as measured in moles times RT over V. Remember that when we use the ideal gas law, the identity of the particles doesn't matter. It doesn't matter whether we have a single component or whether we have a mixture of gaseous components. As long as we know the total number of particles, as measured in moles, we can do calculations on the other properties of gases, in particular the pressure. We can also calculate the partial pressure of just a single component in a mixture, and we can calculate the partial pressure of that single component, which we'll call PA, by knowing the moles of that component times RT over V. When you have a mixture of gases, the temperature will be uniform throughout your mixture, and the volume will also be the same for all of the components in your mixture. Finally, we know that the total pressure is a sum of the partial pressures from our individual components. So PA plus PB plus PC is going to give rise to the total pressure in a system made up of a mixture of gases A, B, and C. Finally, we can calculate the partial pressure of a particular component if we know about the total pressure in a system and the mole fraction of that component, abbreviated by Chi-A. When we calculate the mole fraction, that's going to be equal to the moles of our component of interest divided by the total moles in our system, and we're going to use that to calculate the partial pressure when we know about the moles of our components and the total pressure. Pause the video and try question number 1 and 2 on your own. Question number 1 says, what is the pressure in a 1-liter cylinder that contains 0.250 moles of oxygen at 0 degrees Celsius? So in this question, we're going to use the ideal gas law to calculate a pressure. This question is based completely on things that you already know from our previous studies of the ideal gas law, so that as I plug all of the information that's been given to me into the problem, I have to convert my temperature from Celsius to Kelvin, but otherwise I can plug in for moles, R, T, and V based on the other information that has been given to me. And when I solve, I get a pressure of 5.60 atmospheres. Question number 2 asks me now to solve a similar question for nitrogen gas. What is the pressure in a 1-liter cylinder that contains 0.25 moles of nitrogen at 0 degrees Celsius? This information that I'm going to plug into the ideal gas law is identical to the information that I had in question number 1. And what we know about the ideal gas law is that the identity of the gases doesn't matter. As long as we have the same number of particles as measured in moles, we will have the same properties for our gases. So having a 1-liter sample of nitrogen gas that contains 0.25 moles at 0 degrees Celsius is going to have a pressure of 5.60 atmospheres, just like oxygen gas in question number 1. Question number 3 asks, what is the pressure in a 1-liter cylinder that contains 0.500 moles of a mixture of gases at 0 degrees Celsius? So in this question, we're not told the identity of our gases. We're told the number of particles in units of moles. And remember, with the ideal gas law, the identity of the particles doesn't matter as long as we know the total number of particles in moles. So in this case, we can plug right into the ideal gas law the 0.500 moles that were given in this question. So when we do that, when we plug in for N, R, our temperature of 273 Kelvin, and then 1 liter for volume, and we do the calculation, we get 11.2. So if we compare the answer that we got in question number 3 to the answers that we previously got for questions number 1 and 2, we're going to see the additive nature of the pressures of our individual gases in a system that contains a mixture of gases. In question number 1, we did a calculation on 0.250 moles of oxygen gas and got a pressure of 5.60 atmospheres. In question number 2, we did a calculation on 0.25 moles of nitrogen gas and we got a pressure of 5.60 atmospheres. Here in question number 3, we now did a calculation on a mixture of gases that contains 0.500 moles of particles. and got a pressure of 11.2 atmospheres. Notice that if we add together our samples from question number 1 and question number 2, and the pressures from question number 1 and question number 2, we would get a mixture of gases that contained 0.500 moles and a total pressure of 11.2 atmospheres. In a system, the partial pressures of our individual components can be added together to give rise to the total pressure in the system. The partial pressure of a component, for example oxygen, takes into account only the collisions between the oxygen molecules and the walls of the container as all of our particles bounce around throughout the entire container. Question number 4 says, a 1-liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. If the partial pressure of helium is 341 millimeters of mercury and the partial pressure of neon is 112 millimeters of mercury, what mass of argon is present? So this is a problem where we're going to use Dalton's law of partial pressures. We have a mixture of gases, and in this case we know the total pressure and we know the partial pressures for 2 of our components. We do not know the partial pressure for argon, so in order to find the mass of argon, which is what we ultimately need to solve for, we first need to start by finding the partial pressure of argon. Using Dalton's law of partial pressures, we know that the total pressure in this system is going to be equal to the partial pressure of neon plus the partial pressure of helium plus the partial pressure of argon. So when we substitute in for the values that we know and we solve for the partial pressure of argon, we get 209 millimeters of mercury. We need our pressure to be in units of atmospheres in order to use it in the ideal gas law, but our pressures are additive no matter which units we're using. So that when I convert my partial pressure of argon to atmospheres, I get 0.275 atmospheres. So now that we know the partial pressure of argon, we can use that in order to solve for the moles of argon using the ideal gas law. The volume for our sample of argon is going to be 1 liter. All of our particles have access to the full volume of the sample. The temperature for our sample of argon is going to be 298 Kelvin, which is the same temperature for the entire system. When I substitute into the equation for my partial pressure of argon, my volume of 1 liter, R, and my temperature of 298 Kelvin, I get 0.0112 moles of argon. Because the question specifically asks me for the mass of argon, I'm going to convert that moles of argon to grams using the molar mass, and when I do that, my final answer is 0.447 grams of argon. As an alternative strategy, we could also use one of the application equations of the ideal gas law, where we could use the molar mass of argon to solve directly for the mass of argon in the equation that you see here. You should get the same answer no matter which strategy you use. Question number 5 says, a gaseous mixture contains 0.0446 moles of nitrogen and 0.0265 moles of oxygen in a 1.55 liter container at 18 degrees Celsius with a total pressure of 1.10 atmospheres. What is the partial pressure of each gas? So in this problem, I'm going to demonstrate how we would use mole fraction to solve this. For the information that I've highlighted in pink, where we're told that we have a volume of 1.55 liters and a temperature of 18 degrees Celsius. This is truly optional information. You don't have to have this information in order to be able to solve the problem. Because you have this information, you could solve this problem using the ideal gas law. But be aware that you could also solve this problem if the information were not given to you. If the information were not given to you, you would have to use the mole fraction, and that's the way we're going to solve this example here. So when we talk about the mole fraction, we know that the partial pressure of component A is going to be equal to the total pressure times the mole fraction of component A. where the mole fraction of our component of interest is equal to the moles of that component divided by the total moles in the system. So that if we're calculating the mole fraction of nitrogen, that's going to be our moles of nitrogen divided by the moles of nitrogen plus the moles of oxygen in our system. So that means we're going to have 0.0446 divided by 0.0446 plus 0.0265. That makes our mole fraction of nitrogen 0.627. If you notice, the mole fraction is a little bit like calculating a percent, except you're not going to be multiplying by 100. The maximum value that you can have for a mole fraction is 1, so that all of the individual mole fractions that you would have would add up to a total of 1. So when we use this information to calculate the partial pressure of nitrogen, we're going to take our total pressure, which was given to us in the problem of 1.10 atmospheres, times the mole fraction of nitrogen, which we just calculated, of 0.627. And when we do that calculation, we get 0.690 atmospheres, which is the partial pressure of nitrogen. Now that we have the partial pressure of nitrogen, the easiest way to get the partial pressure for oxygen is to use Dalton's law of partial pressures and recognize that we know the total pressure and the partial pressure of one of our components, and we can set up the equation to then solve for the other component in our mixture. In this case, our total pressure is equal to the partial pressure of nitrogen plus the partial pressure of oxygen. We know the total pressure and we know the partial pressure of nitrogen, so we can solve for the partial pressure of oxygen to be 0.410 atmospheres. If we were to calculate oxygen's partial pressure using its mole fraction, we could get the mole fraction of oxygen by taking 1 minus the mole fraction that we calculated for nitrogen. So in this case, 1 minus 0.627, and we would get 0.373 as the mole fraction. A mole fraction value has no units because it's a ratio. Question number 6 says a 1.35 liter mixture of gases contains nitrogen, oxygen, and helium at 25 degrees Celsius. The partial pressure of nitrogen is 215 torr, the partial pressure of oxygen is 102 torr, and the partial pressure of helium is 117 torr. We have several questions that we need to answer as a part of this question, and part A asks, what is the total pressure? In this case, we're given the three components in our mixture, and we're given the partial pressure of each, so our partial pressures are additive. When I add up those partial pressures, I get a total pressure of 434 torr, and when I convert that to atmospheres, I get 0.571 atmospheres. Part B says, what is the total amount of moles of gas present? I can answer this question if I know the total pressure in the system. I can plug into the ideal gas law to calculate my total moles. So when I plug in with my total pressure, my volume, R, and my temperature of 298 Kelvin, I get a total moles of 0.0315 moles. Part C asks, what mass of nitrogen is present? And there's two ways that we could go about solving for nitrogen. We could use the ideal gas law and solve for our moles of nitrogen by plugging in the partial pressure of nitrogen in units of atmospheres, along with our volume, R, and temperature, which would allow us to solve for moles, and from there we can convert from moles to grams using our molar mass. As an alternative, we could also use one of our application equations of the ideal gas law, where we could solve directly for the mass of nitrogen by plugging in for the molar mass of nitrogen, the pressure, the volume, R, and T. When we do this, remember that nitrogen is one of our diatomics. We see it with its chemical formula, but make sure you account for that when you calculate its molar mass. When we plug in for the molar mass of nitrogen, which is 28.02 grams per mole, our partial pressure of 0.283 atmospheres, our volume of 1.35 liters, divided by R, times our temperature of 298 Kelvin. Make sure you use parentheses around your denominator, and when you solve, you should get 0.437 grams of nitrogen.